So let's talk a little bit about the mechanics of a joint. So all of our joints are functionally levers, and there are three different classes of levers. So a lever has three parts, a fulcrum. So the fulcrum is kind of the center of the seesaw right here, where the pivoting action occurs through an axis. An effort arm. The effort arm is the arm putting in effort. So this might be a muscle pulling on here, and the arm length is the length from the fulcrum to wherever that muscle or effort is being inserted. And then the resistance is the resistance arm, which is the load that's trying to be moved, or maybe the force of gravity working against you. And the resistance arm is the distance from that resistance point to the fulcrum. So there's three different classes of levers, first, second, and third. And you can tell them apart by the order of these three things. So all you need to know is which one is in the middle, because the two on the side can be flipped and it would stay the same class. So on a first class lever, we have the fulcrum in the middle, and this is your typical seesaw. So we've got our fulcrum in the middle, resistance on one side, effort on the other side. So the child puts in effort against the ground to push themselves up. Moving the other child, that's the resistance. So an example of a first order or first class lever in your body is when you tip your head back to look up at the ceiling. So what's happening here is the muscles in the back of your neck are pulling down. That's your effort. So your effort arm is this distance from that insertion to the fulcrum. The fulcrum is going to be where your head is attached to your spinal cord along your neck. And then the resistance is the weight of the rest of your head being pulled down by gravity. A second class lever is going to have the resistance in the middle. And this is your typical wheelbarrow. So in a wheelbarrow, your fulcrum is down here at the wheel. That's where it actually lifts off the ground. You have to put in the effort here by lifting up the wheelbarrow. And then the resistance is the weight of whatever is in your wheelbarrow. So an example of that can be seen by the leg here. So if you sit down in a chair with your leg at a 90-degree angle, and then you lift your entire leg, so not kicking out, but lifting all the way up, the effort is actually coming from the contraction of this muscle, the quadriceps, but the tendon is going to push that effort all the way out to here. So my effort is out here. My resistance, again, is the weight of my leg, pulled down by gravity. And the fulcrum is now at the gluteus, at the hip joint, where the leg is actually moving. And then a third class lever is going to have the effort in the middle. So this could be exemplified by kind of rowing a canoe. So this guy's in a canoe and here's his paddle. The fulcrum is at the hand. This hand isn't actually doing any of the effort, it's just holding it in place. And he pulls back with his other arm here to push the paddle through the water. And the resistance is the water resisting the movement of the paddle through it, which will propel the boat forward. So we can see this in our biceps. So this would be if you were flexing your biceps. So the effort is through the bicep muscle, but the bicep muscle inserts here on the bone, so that's actually in the middle. So it's going to be pulling your arm this way. The fulcrum is the elbow joint, and then the resistance is either the weight of your arm with gravity, or you could put a dumbbell in your hand, and that could be the resistance as well. I'm not going to have you calculate mechanical advantage, but it is something I want you to be aware of. So mechanical advantage is the output force over the resistance force. So on our arm, here's our third class lever. Our resistance arm is the distance from the fulcrum, so from the elbow to the resistance. So in this case, maybe they're holding a dumbbell. When this resistance arm is really big, we're going to tend to have a low mechanical advantage, which means we don't have a ton of power. but usually that means that this joint can move very quickly. So most joints in the human arm and leg typically have a low mechanical advantage but are very fast, which is something we've adapted to, being kind of high-speed runners or distance runners. A different example would be a digging animal. So this is going to have a high mechanical advantage. So the resistance arm is actually from here to this fulcrum, and that's relatively shorter. And so when we have a lower resistance arm, like somebody who digs, they don't need to dig fast. They need to dig powerfully to move a lot of dirt. So they're going to typically be slower, but have a high power, high mechanical advantage. The structures of our joints influence how they function. So this goes all the way back to the physical structure influences function. So some of the aspects of anatomy that influence how our joints function is the actual bone structure. So if you extend your arm, unless you have an anomaly of your skeleton, you probably can't extend your arm past 180 degrees or much past that. And the reason for that is because your elbow is in that olecranon fossa, and you can't move it because of the physical structure of the bones. The strength of our ligaments. So if we look at our knee joint, we can't hyperextend our knee because our ACL ligament pulls tight. And if you do hyperextend your knee, what you're going to do is you're going to damage your ACL. And then our joint motions are limited by the actual movements of our muscles and tendons. So if you don't have a muscle to pull on your bones, you're not going to be able to move the bones in that location. So all joints are going to have axes of rotation that pass through the bone. Some joints will be monaxial, meaning they only have one axis of rotation. Some joints will be biaxial, meaning they have two. And then multiaxial is going to mean 3, so this is like your shoulder and hip. There's no more than 3 axes because we only have 3 dimensions. So take a moment and reflect on the anatomical aspects that affect joint motion.